I'll talk today about a recent paper that came out titled Modular Factorization of Superconformal Indices. It's not very safe. Okay, so I don't have to explain it. One of the central questions in our field is about the nature of the microstates of the counted by the Bekenstein Hawking measure. And within the context of string theory, ADS CFP provides at least a partial answer.
There's no dongle as part of the laser pointer. Usually they have one attached, right?
I think I'm going to manage very carefully. First, I need to do things slowly. All right.
Don't ask hard questions.
Yeah, hard questions if you just make it vanish. Questions go away.
So within string theory, specifically within the context of ADS CFP, two-dimensional CFPs have played a special role. And well, especially for questions in quantum gravity. Why is that? Well, I mean, perhaps people think about this otherwise, but I think it can be boiled down to modular invariance or covariance of torus partition functions, or more generally indices, of two-dimensional CFTs, which transform under the modular group. This is a very powerful symmetry. For example, the S transformation in Asymptotic leads to formula for the entropy of high energy states, the universal formula. And more generally, at least for holomorphic partition functions, holomorphic CFPs, you can write an exact expression for these partition functions as an average over the modular group. And these two facts have a very interesting quantum gravity relation. So the Cardi formula famously matches with the Bekenstein Hawking entropy of a special class of black holes. And this average of the modular group can very naturally be interpreted in terms of a gravitational path integral, because this same concept also labels black hole saddles in the Euclidean sphere.
Are you going to be a little more precise what you mean by gamma infinity minus O2?
Yeah,
because as stated, I think it doesn't converge.
No, I'm not going to be more precise.
Okay.
Sure.
So it doesn't. I mean, this is a congress series, and it doesn't converge, and it requires a long song and dance to.
Yeah, that's right.
Okay.
So this is just to say that I mean, certainly these expressions an expression of that type arises from modular invariance.
Yeah, but for example, these black hole saddles, there's not actually a full SO2 orbit over it. There's some modulo, some subgroup.
Well, that's the gamma infinity that you mean, where you're meaning that there's a further reduction.
Yeah, I think there's a further reduction.
There's a further reduction. Okay,
so the points in the coset are the cycles that you fill in, right?
That's right. Yeah. That's right. So it's the fact that it has to do with the T transformation on the boundary.
Yes.
And I think it can be interpreted as adding contractible cycles in the block.
Okay, well let's see. So you're going to write that down.
No, I'm not going to write it down. Sorry, because it's not that. This is just motivation. And this is not. My talk isn't about this. It's just some historical effects. Yeah, I'm not going to be precise about those. In fact, I can't be precise about it because I don't know the full details. So recently, there has only recently there has been similar progress in ADS CFT for higher dimensions than 2 on the boundary. And the case that is of relevance for, or at least motivates our present work, is the standard, the prototypical ADS CFT correspondence between the n equal to 4 theory and type 2 supergravity. In particular, it is expected that some ensemble of 1/16 BPS states in the n equal to 4 theory should somehow be dual to a Kerr-Newman BPS black hole in ADS. And one would like to study these supersymmetric black holes using protected CFT quantities, which, and one such protected quantity is the superconformal index, which counts these BBS states with signs. So previously, it was thought that precisely for this reason, that it counts BBS states with signs, that it doesn't capture degeneracies and therefore cannot capture the black hole entropy, the Bekenstein-Hawking entropy. But a new insight has actually allowed the exact computation of this entropy from the index. This is sort of, I'm not going into any details of this, but this roughly motivates our work. And why is that? Well, essentially every derivation that there were three main references here, and essentially every of those derivations, even though they're quite different superficially, so the common denominator is that they rely on a type of modular property of the elliptic gamma function. So I'm going to define this function in the main part of my talk. But yeah, why do I say this is a modular property? Well, there's this typical inversion of chemical potentials that we also know from SL to Z, from the action of SL to Z. But of course, we don't expect really modular symmetries because the path integral that we're talking about now takes place in S3 plus S1, and space and time dimensions are not on the same footing. And as I will argue in more detail, this is related to the fact that there's actually 3 functions involved here instead of 2, which you would expect for covariance or invariance. And in addition, there are 2 modular group actions at work here. So let me just briefly indicate which they are. So we'll see that there's an SL3Z, which you can interpret as the fact that the transformation that exchanges tau and sigma relates the 2 gamma functions on the right-hand side here, and that more generally can be thought of as an SL3Z transformation. And there's an overall S transformation between right-hand side and left-hand side, and that can be thought of as this SL2Z. Again, the aim of this talk is to make this precise and understand this physically or geometrically in a similar way as we understand modular invariance in 2 dimensions. And this is very much inspired also by an article of Abhijit's.
Yeah. Question, yeah. So I thought that one derivation, of course, you could do was just take the index and just evaluate it by brute force, the degeneracy, which is something that when we wrote our paper, we just didn't do. As you said, we had a mistake. But one could just evaluate it. But the difference I thought with the Cardier thing is that in this case, one has a specific index which one can compute, then the path integral formula, and then one wants to check the asymptotic of that specific index, as opposed to arguing that every theory with some central charge or something will have the right result. So does one necessarily need the modular property as a general property of the index, or does one need a property of a particular index?
So you're asking, are you asking if it's specific to the input flow?
Yeah. So that may be one way of saying. Because in evaluating this function field, you are only looking at the index of one theory. Right? It wasn't that you were trying to say looking at the index, looking at some general index and evaluating.
No, so my talk will be about general indices. And in fact, I mean, this elliptic gamma function is sort of a main, plays a role in for arbitrary gauge theories. So in fact, this elliptic gamma function is not the index of the n equal to 4 theory. The n equal to 4 theory consists of a, right? As you know very well. And but you can view the elliptic gamma function as a building block of the index of any gauge theory, and this property, the asymptotics of any of those indices can be computed using this specific property.
So as Sam said, many of these references use this property, and once you understand this, you get this result for free for
almost all the cases which have appropriate properties.
I see.
In fact, the supergravity result basically corresponds to taking these two gammas on the right hand side to one.
Setting it to one.
That's
Yeah,
right.
exactly.
Just have the cube.
Exactly.
May I ask a very naive question?
Yes.
So, what is this? Why does 2 gammas come on right hand side?
Yeah, I'm going to explain.
Okay.
I'm going to explain.
So it's just an observation that they started from.
So far people have used this to compute the asymptotics very instrumentally, but the motivation to understand where this comes from geometrically or physically is ultimately motivated by the question if we can, go a bit further than just the asymptotics and reproduce more general results that are available in two-dimensional CFPs, such as this, sum.
So originally it's just an observation that people made.
So far, it's been a technical tool, and it's been also approached in that way. I think actually only in the paper by Abhijit has there been more discussion of a sort of more physical interpretation, geometric interpretation.
Sam, one question. Why don't you write SL3Z symmetric Z cube?
Yeah,
You don't like that?
I'm not going to take the Z cube
Okay.
into account.
But that is there, right?
That is there,
Yeah.
that is there, yeah. This is So I'm first going to talk about some geometric things to first introduce some geometric story before we turn to these indices. And the geometric story that I need is known as the Heegaard splitting. So what is a Heegaard splitting? Well, this is the statement that in fact any free manifold can be split into two genus G handle bodies. Genus G handle body is just a Riemann surface that is filled. The claim is that if you glue two such genus G handle bodies with an orientation reversing diffeo, you can glue any, you can get any free manifold. And this F is classified by the mapping class group of the boundary Riemann surface. Okay, so a simple and relevant example is is the genus 1 Heegaard splitting of the free sphere. So you can think of the free sphere inside C2 through the following equation. And this equation can be read as a torus vibration over an interval, where the torus is formed by the phases of Z1 and Z2. And one phase collapses on one side of the interval, the other phase collapses on the other side. So that means that at the endpoints of this interval, we can think of the geometry as a disk times a finite circle, the finite phase. But you see that because the one phase shrinks on one side and the other they exchange, and this can be thought of as the S transformation, which is indeed inside the mapping class group of the torus. Now, more generally, of course, we can consider genus 1 Heegaard splitting for more general SL2Z transformations. In general, you will get a length space. So I've denoted the Heegaard splitting here on the right. So here is a two solid tori, 2D2 cos x1 geometries. I've indicated the contractible cycle by mu and the non-contractible cycle by lambda. And then, one identifies these two on their boundaries for general SL2Z transformation. And this gives rise to a length space, which can be thought of as this quotient of S3. Now, the non-contractible cycles are defined only modulo the contractible cycles, because if I add a contractible cycle to a non-contractible cycle, I still have a non-contractible cycle. This leads to a redundancy in F in the following way. So here the gamma infinity thought of as a subgroup of SL2Z, which fixes mu and shifts the non-contractible cycle by multiples of the contractible cycle. this redundancy can be expressed in the following way. So the manifolds glued with the transformation f prime and f give rise to the same topology if f prime and f are related by this conjugation. Well, it's not a conjugation, so it's a multiplication by gamma on the left, which adds the contractible side on the left side of curves and gamma tilde on the right, which is on the right side of curves. And indeed, if you just work this out, you'll find that this transformation shifts q by p, and that's of course gives also rise to the same length space if you look at the quotient definition. Okay, but as I mentioned, we're interested in four-dimensional theories and four-dimensional indices, and these take place on these four manifolds, L, P, Q, generally times a circle. And it will not be surprising that these manifolds admit a similar decomposition. In this case, we have an extra circle. So instead of a solid two torus, we have a disk times a two torus. You just add a circle. And now the gluing transformation that combines these two, that acts on the boundary T3 of these geometries, in general takes a value as a freezing. And now you may ask, so how is the topology of this MF encoded in a general SL-freezing transformation, similarly to how the topology here, P determined by P and Q, is encoded in SL-freezing transformation.
What is O there? GO?
So O is here. O here is the orientation reversal. So sometimes use F to denote the orientation reversing transformation, and when I talk about something SL-freezing or SL-freezing, I'll denote it by G. So in this case, we similarly have equivalences. So now the transformations that preserve the contractible cycle are more general. So in this case, right, we can still add the contractible cycle to any non-contractible cycle and still have a non-contractible cycle. This gives this Z2 mu that I've noted there. But in addition, there's also an ambiguity now in the non-contractible cycles themselves. We have an SL2Z acting on them, right? So the claim is that in this case, any manifold glued with some transformation f prime or f give rise to the same topology if f prime and f are again related in the same way as in the previous case. Okay.
I'm sorry, yeah, I actually completely got lost here.
Oh,
I think it would be easy to get. So LPQ previously was a two-manifold length space?
No, three manifold.
Wasn't it a...
Sorry. So it's...
Oh, it was, okay, okay, very good. So then you said, so now you're on 4 dimensions?
Yes.
Okay, and we're heading to 5, but...
No, we're heading to 4. We're staying at 4.
Okay, wasn't it a 5 sphere we wanted?
No. I want 4 manifolds.
Oh, sorry, we wanted the thing. Oh, okay, so we want S3 plus S1.
Yes. Ultimately, or more generally, length space.
I understand. Of course.
Yeah. So here, just a statement is that the topology only depends on how these contractible cycles are glued into each other, and I can show there's an ambiguity in how I treat the non-contractible cycles, and this is parameterized by this subgroup H, which is SL2Z times Z2. Okay, and so how does this, what does this tell us about this general SL3Z transformations? Well, it turns out that for a general SL3Z transformation, there always exists this choice of H and H tilde for some P and Q, such that I can write the general SL3Z gluing in the following way. So I can write it as this essentially SL2Z transformation that is that just acts as the identity on one of the circles. So this is how you can see that a general SL3Z transformation indeed gives rise to a geometry of this form. Because the lower part is just what glues the lens space, and the one circle goes along for the length.
So you are saying if you think of this as an equivalence relation, there always exists a representative
That's
of the equivalence class which looks like
That's
this.
it. That's it. Okay. We want to be a bit more general. We don't only want to talk about topology when we're going to compute indices. We want to add complex structure moduli to these manifolds in which the partition functions will depend. And how do we do that? Well, on the left-hand side, we can introduce this secondary Hopf surface. There's some complex manifold with topology LP, Q times S1, but it in addition has additional structure which are labeled by these complex structure moduli. Here, tau hat and sigma hat you can think of as squashing the lens space and fibering it non-trivially over the S1. And I've also added some, in this notation, rho hat, I've also added some holonomies that will be associated to global symmetries or some vector bundle over the Hopf surface. And yeah, so these are holonomies for those global symmetries along the S1. Okay. On the right-hand side, I define this Heegaard splitting as the manifold MF that we saw previously, which glues together two D2 cross D2 geometries. But now I also add complex structure moduli. I also do complex structure moduli on D2 cross D2, which I denote by rho. You can think of these guys in the following way. So it's a tau and a sigma. The sigma is just a normal complex structure on the torus, and then tau can be thought of as this combination of two real parameters, alpha and beta, that tell you how the disk is twisted as you move along either side of the torus. Okay, I can write these moduli also in a projective way, and then the SL3Z action, so the gluing action that I sort of implicitly use here, this SL3Z acts on rho by left multiplication of this vector S. Okay, and I have to, if I want to glue these two D2 cross D2 geometries together, I have to make sure that upon gluing, their moduli agree, and that is ensured by taking the moduli of the second D2 cross D2 geometry as such. Okay, and finally, so the moduli associated to this Heegaard split into the D2 times D2 geometries and rho hat, they are generally not equal, but there's some linear relation between the two. That will not be important for the rest of this talk. Okay, so now consider the following.
Let's go back. So, could you remind me again? So, your rho was just or the sigma was just the modulus of the torus, a regular one. What was the tau? I mean, I can see that you're defining it like this, but how do I think about it geometrically?
So it's parametrized. So it's a vibration of the disk over the torus, where as I walk around either side of the torus, I rotate the disk rotates by a certain amount.
So it somehow describes how the disk is fibered over the torus.
That's right.
On the other hand, the sigma and the tau, they appear completely symmetrically, at least eventually, in this elliptic gamma function. So,
yeah.
so they here are being interpreted geometrically differently.
That's right. That's right.
And it's somehow mysterious almost that they are appearing equivalently, or there's some, or at least that would anyway take a different geometrical construction to understand.
Yes, that is indeed a bit surprising. It's so. This is known to be true.
Yeah. I'm sure. Just
yeah. Maybe
I missed the torus.
No, you're right again.
Whenever there's an SO2, there's a torus, right? That's a theorem.
No, you're jumping way ahead, but indeed this symmetry in tan sigma is a bit surprising. I think the original authors of the paper where this thing is computed make this observation and also not able to fully explain it. I'm also not completely fully aware of the explanation. But yeah, let's see. Maybe.
Quick question.
Yeah.
So is this, with this topology, is this all the metrics in three manifolds, or is this a special subclass of metrics?
Sorry.
If you fix the topology to be this
Yeah.
length space times S1,
Yeah.
then you're looking at a special subclass of metrics, or is this all the metrics?
I think this is probably a special subclass of metrics.
There's also only the complex structures.
Right,
Yeah,
that's right.
And we're only talking about complex structures, exactly. Yeah.
Right.
Wait, just to answer Finn's question, can I think of this parameters also as, let's say you have D2 and a S1 and an S1,
Yes.
right, a disk, right? So one of the S1 is going to be, let's say, the S1 of the final S1 that is just decoupled, right? So I express how these other two circles,
Yes.
one that is non-contractible and the other that is contractible,
Yes.
are fibered over it
Yeah.
in the sigma and tau way.
Yes.
So in that sense, they appear symmetrically because the way you will glue it on the left hand side, the contractible will become the non-contractible one, and the non-contractible. I mean, very roughly, one could think of that as the origin of the symmetry between sigma and tau.
I don't quite follow you, but I can see that has to be somehow. Drawn.
Okay. Thanks. Yeah, I think. Yeah. So now we had already seen that this action where you sandwich some gluing transformation between H and H tilde inverse, that gives rise to the same topology. Now I'm gonna get the same Hopf surface. I have to supplement it also with an action on the modular. The claim is that this combined action on this Heegaard splitting gives rise to an identical Hopf surface. Or in other words, any given Hopf surface for fixed modular can be split in a variety of ways, which are labeled by this H and H tilde. So this is some type of geometric action. It's not a large diffeomorphism of the Hopf surface. It's an identical Hopf surface. Rather, this action reflects ambiguities in the Heegaard splitting of this Hopf surface. And to illustrate that, let's look at
claim mean is that it's your claim or is it a theorem?
No. I think this is just
true. The literature.
Yeah, I'm gonna sort of convince you with an example that this is true. So let's consider indeed two such Heegaard splittings of a primary Hopf surface, which is just the topology S3 cross S1. Okay, so we've already seen that S3 cross S1 can be obtained by exchanging a contractible cycle with a non-contractible cycle. So let's just keep the first circle over there invariant and exchange the last two. That gives me one Heegaard splitting of this geometry in terms of these D2 cross D2 geometries with moduli tau and sigma. And then the second D2 times D2 will have sigma times tau, such that the cycles are appropriately matched. But, okay, I can also consider, according to this claim, a different Heegaard splitting. And let's take this H and H tilde.
Sorry, just one observation. So I think, here you can see that this left-hand picture is symmetric in X2, X3 exchange, right? Yes. And if you look at the map between sigma tau and X3, you will swap sigma tau as you exchange X3. Is this not correct?
Yeah.
Yes.
Right, but it's now explained in terms of this ambiguity in the splitting, which I guess is sort of a new ingredient.
Sorry.
But yeah, you're right. That yes, this at least gives some kind of symmetry between the sigma and tau.
Oh, in that sense.
Okay.
Yeah, but no, but we're talking. Okay, I see. But I think Finn's question was about a single D2 cross D2.
Not a single, the final one, the final geometry.
Oh, that was how I interpreted you.
Right, I mean, but I don't know, but there was a picture there where
No,
the tau was
I think
introduced in a
clearly-
way that was very different from the sigma.
I think for the full geometry, it's clearly symmetric, and that is also reflected in the, and that's not a mystery.
Yeah.
But there's actually already a symmetry for the,
Yeah. I mean, one-sided geometry is clearly not symmetric between sigma tau exchange.
yeah, but that's true, but the index is symmetric under that exchange.
Only on one side?
Well, sorry, I should be a little bit more precise. So it's the holomorphic block, let's say, the D2 plus D2 partition function, up to a phase is invariant under this exchange. Okay, sorry. Okay. I misread them. No, I'm
No, that doesn't
misremembering
sound
something. No, that only happens in the very special case of a vanishing R charge. Right. And, okay, sorry. No, it's generally not.
Yeah.
Okay. Sorry. Yeah. So I'm writing here according to this claim, a second Heegaard splitting, where I act with this S1 free, which exchanges the two non-contractible cycles on the T2, just exchanges X1 and X3. So these twos, D2 plus D2 geometries have different moduli, now given by tau over sigma -1 over sigma, etc. But I'm also changing at the same time. So I'm having an action on the moduli, but I also have an action on the gluing transformation, such that ultimately X2 and X3 are again exchanged. So it's very clear that if you combine the action of a large diffeo on the D2 plus D2 geometries with the appropriate change of gluing transformation, that this gives the same closed map. That's it. So this is to convince you of the general all right. Okay, a little bit more review. So these, as I already alluded to, these four-dimensional input one theories with a U1R symmetry can be formulated, can be put on these secondary Hopf surfaces while preserving supersymmetry for general values of the moduli. And the supersymmetric partition function only depends holomorphically on these moduli. So it's almost topological. It only depends on the complex structure moduli. Now, the path of the integral on this Hopf surface can also be thought of as an index, where the index is over the Hilbert space of the theory defined on the length space. Here, the J1 and J2 and cube A and R are the various global symmetries of the theory, and the fugacities in the index are exponentiations of the complex structure moduli of the background geometry. Right? And the usual arguments imply that this thing only receives contributions from BPS states and is therefore invariant. So just to be a bit more, just to be sure that this is very explicit, one can compute this index, an exact formulas for this index for general input one H theories. So here is an example of such a formula for the superconformal or S3 plus S1 index. So what happens here? Well, we have a vector multiplet contribution that consists of these elliptic gamma functions and some cube Pochhammer symbols. It's not too important. Chiral multiplets and various representations of the gauge and flavor symmetry also contribute through elliptic gamma functions. And let me also finally define the elliptic gamma function. So the elliptic gamma function can be written as this statistic exponential or as a double infinite product. Okay, and there's very similar expressions also for lens indices or ST plus T2 indices. They're structurally very similar to this formula. So let's get a little bit of intuition for where this formula comes from. So as I said, you can compute it in two ways. you compute it as in terms of the index, the trace formulation, you can construct the BPS Hilbert space at the U-free fixed point. Then you can think of these double infinite products that appears for all these multiplets as due to the fact that there are two BPS derivatives. So, of course, there are 4 space-time derivatives, but only 2 of those have the quantum numbers to contribute to the index. And then finally, this contour integral projects onto gauge invariant states. Alternatively, and also an important perspective, is it can also be computed as a supersymmetric path integral for localization. And what happens in that computation is that there is an equivariant localization such that the only field configurations that are localized on the north and south poles of this Heegaard splitting contribute to the index. And in this case, these doubly infinite products can be thought of as due to the mode expansions of the remaining T2. And then this contour integral is the remainder of the full functional integral reduced to flat dimensions. Now, this last perspective.
Can I ask a question? Sorry. This north and south pole anchoring.
Yes.
Where does it get manifested in the formula?
So this gets manifested in the localization computation of the path.
I guess the expression that you wrote previously for the full answer,
Yes.
not having obviously something times something else.
That's
It
true.
didn't look sort of, one might have thought it was holomorphic times anti-holomorphic or
Now
whatever.
we're getting it. You're one step ahead of me, but indeed, this is not obviously written in that form, but in the actual computation that leads to these formulas, there is contributions from North Pole and from South Pole, and they combine together into these elliptic gamma functions. So but there is actually I agree that this is not a manifest way of writing that expression, that factorization, but there is a way to make this manifest, and that is what's known as this holomorphic block factorization, which tells us that, which is the statement that the index can be written as a summation over factorized expressions. And indeed, you can think of this, what is known as a holomorphic block, as the D2 cross D2 partition function. And I've written a little s there to indicate that in this standard story of holomorphic block factorization, there's actually it's perhaps not it's not quite the standard Heegaard splitting. It's the holomorphic blocks that appear in this formula are the partition functions on a D2 cross D2 geometry with moduli S1 free times 1. Okay, that was previously just used, but not really explained. And so we say, well, this reflects a very specific Heegaard splitting of the Hopf surface, this factorization. And that's fine. This is a Heegaard splitting. And this then provides a complete physical interpretation of this property, of this basic elliptic gamma function property that I showed in the introduction, where you can think of the left-hand side as a superconformal index of a vanishing R-charge chiral multiplets. And the right-hand side corresponds to the D2 cross D2 partition functions, which have been computed independently on this D2 cross D2 geometry of moduli S1 free. Okay. So this is so to come back to your question, I think this is one way of thinking of. This is the physical interpretation of that modular property. This is what there are probably more interpretations, but this is for me the most transparent physical interpretation of this thing. Okay. Okay, so now to the new thing. So then you might ask, of course, that that's how I've been suggesting it also. Is there something special about this S13? And we claim essentially no. So in particular, to explain that, let me just introduce different notation for this index. So instead of reflecting the Hopf surface by PQ and rho hat, I'm going to reflect the Heegaard splitting, which is this gluing element, and the modular rho associated to the D2 plus D2 geometry. And then we have that this ZF prime of rho prime is equal to the ZF2Q of rho for any such transformation, simply because that's just by definition, because these two Heegaard splittings lead to an identical Hopf surface. So the Hopf surface is unchanged. So this is just, in some sense, a trivial statement. But it becomes non-trivial at the level of the factorized expression. So I'm just going to plug in I'm going to assume factorization of both the left and right hand side associated to the relevant Heegaard splitting, and then I get an equation of this type where I have some general H action on rho, which generally acts like SL2Z on sigma, and then some shifts of tau corresponding to the Z2 part. There's this product of those two factors, and this should then be equal, according to our claim, to the untransformed gap, right? Because these Heegaard splittings produce the same Hopf surface.
So this,
Yeah.
I mean, this factorization you cannot quite do for any element of asymptotic density.
No, that's right.
There is a cohomological obstruction to that.
That's exactly. Yes. So I'm coming there. So this conjecture is too general. We're going to see how it has to be refined. But this is sort of a naive claim that you might make.
Did you ever define the P, the script P?
Yeah, this is some phase.
I
So
assume
the
that's what you
factorization.
said. You didn't define it, did you? Or you didn't?
No, I didn't. So it also appeared here. So the factorization in 4 dimensions is not perfect. There's this phase which turns out to encode the global anomalies of the theory, total anomalies of the theory. Yeah.
Are they related to the cubes?
Yes.
The cube? And so therefore they're also an anomaly polynomial for this thing?
Yes. So for the you mean that for this more general factorization here, there will be an anomaly. So the phase there can still be interpreted as an anomaly. Up to some changes of variables, basically. Okay, so to come back to Abhijit's question, so well, how can we be sure of this? So how are we going to test it? And the first test is a physics constraint, which may be a bit tangential at the moment, but which led us to understand this better. So we want that this index is independent of the boundary conditions on the holomorphic blocks, right? Because ultimately the compact space partition function should not know about the boundary conditions. And indeed, so I didn't explain, but this alpha labels some boundary condition on the holomorphic blocks, and the sum over alpha, of course, ensures that the index doesn't depend on alpha. The full index doesn't depend on this boundary condition. But it turns out that there's sort of a refinement in a sense of these boundary conditions. Namely, for each given multiplet in the theory, there exist at least 2 BPS boundary conditions. It can be essentially thought of as a Neumann-Dirichlet boundary condition. So let me just assume the same boundary conditions for all the multiplets of the theory in one case and the other in the other case, and denote the respective holomorphic blocks by the D2 plus D2 partition functions by B and C, as in here, and we want that this product here doesn't depend on the boundary conditions. So we want that the product of the two is the same, potentially up to a phase which is independent of alpha. So this is a constraint that we want to impose, which we want to solve in terms of the H and H still. Okay. So we want to solve for H and H tilde for some fixed index, for some fixed Leuven transformation. And it turns out that the result can be understood geometrically. So the result is that the index can be split into holomorphic blocks associated with Heegaard splitting, such that the Leuven transformation associated with the Heegaard splitting F prime is of the following form. So this is some subgroup of SL3Z, where the top 2x2 block is an SL2Z transformation, and the bottom row contains two Z2s, and we call this F. Okay. It's similar to the subgroup H. It's isomorphic to the subgroup H, but it's a different embedding SL3Z. And geometrically, what it does is that in H, H was the subgroup of SL3Z that fixes the contractible cycle, mu. F instead is the subgroup which fixes the cycle lambda H. So it fixes a non-contractible cycle. Okay? And it acts in some way on the remaining cycles as an SL2Z cross T2 transformation. So the idea is that this fixed cycle, so we're constraining the gluing transformation such that one cycle is fixed in the gluing, and that then is naturally identified with the time circle in the full Hopf surface. And so the idea is that these solutions, H and H tilde, which solve this condition, they actually parameterize ambiguities in how you embed the time circle in the Hopf surface inside these D2 cross D2 geometries. And clearly there are sort of multiple ways, because there's a D2, and these multiple ways can be parameterized by these pairs H and H for a fixed Leuven transformation.
I'm sorry, I'm lost again. So we're using a time circle within the Hopf surface. I thought that there was an S3 or whatever lens space plus S1.
That's right.
And if that is one that is called the time.
That's what I think.
So it's not just a feature of the Hopf surface itself, it's how you take that as X plus 1 and fiber it over the lens space.
Yeah. I mean, well, the Hopf surface contains that circle. Yeah. It's a form of it contains that circle. And I call it a time.
I'm sorry,
Okay, so you can just solve this explicitly. So you can.
Sorry, Sam. What is the statement that this F prime, if it is of this form, then what can you do?
Then I can factorize the index into holomorphic blocks BH and BH tilde. Then I can factorize the index. So I can't do it just
You really factorize the index? You don't factorize the index into some of such terms.
No, I factorize it into a sum of such things.
So you didn't factorize the index, you factorized it into a sum of such things.
That's right.
Blocks.
So the condition for that is that the phase was independent of alpha. Something was independent of alpha, right?
So okay. Yeah, I can. Yeah, so the condition that has to be, well, this is the condition we want to solve. So we want to ensure that the product of these blocks with either Neumann boundary conditions, let's say the chiral multiplets or Dirichlet boundary condition is not chiral multiplets, that the product doesn't depend on that. and that turns out to constraint H and H tilde in a way that can be geometrically understood as this statement that there's a fixed cycle between.
So this gluing also prefers a particular representative of this equivalence class. The equivalence class of all the transformations which keep the topology.
Yeah, but there can be multiple. So there's not a unique H and H tilde corresponding to this.
Okay.
So for fixed FPQ, there's a modular family of H and H tilde that will lead to modular factorization. If I allow F to vary, then clearly there will be a unique pair H and H tilde. I will come back to it. But for fixed FPQ, there's a family of H and H tilde that solves this condition. And the claim is that family, sort of, how you understand that geometrically, is that you can embed the tiny circle into these D2 plus D2 geometries in multiple ways. Right. So the explicit solution, so you can just solve that. And the explicit solution looks like this. So I have some H, which is essentially completely free. So it's an SL2Z transformation in the corners. And then there's some Z2 part. And this Z2 part is just some parameters by some free integer that I call C. But then this H tilde is completely determined in terms of H. And in terms of the parameters P and Q and R and S that are part of this gluing transformation that creates the length space. And this is the explicit expression. So K, N, L, and M have to satisfy this SL2Z conditions. So I want to make a bit more precise how these things are parameterized. So it turns out to be useful to first of all parameterize C as some linear combination of M and N, which is possible because M and N are coprime integers, for some free integers A and B. Now, there's a periodicity of the holomorphic block, which is the periodicity of the tau to tau plus 1 and sigma to sigma plus 1. This essentially fixes K and L. So, and K tilde and L tilde, because I have periodicity on both sides. And it also fixes the value of B between 0 and N. And then A is still a free integer. So then we can say that actually H and H tilde that are written here are parameterized by free integers, M, N, and C. And the SL2Z conditions that I've written there can be summarized into a single coprime condition. That is sort of the benefit of parameterizing C in that particular way, because you see that this essentially is the coprime condition of the second, the SL2Z condition of the second tilde matrix, but because n factorizes automatically also solve the first coprime condition. So these solutions are parameterized by free integers with this specific coprime condition, and I can write it a bit more concisely. So I've written here the set of H and H tilde modeled out by this periodicity under tau to tau plus 1 and sigma to sigma plus 1. And so the free integers that satisfy this condition can be thought of in this particular way. So you think of it as a union of congruent subgroups of SL2Z. Now that's not too important, so I'm not going to spend more time on defining that, but just to say that there's some concise way of referring to free integers that satisfy such a condition. All in all, this leads us to the modular factorization conjecture, which is the statement that a given length index can be factorized into a family of holomorphic blocks, which are labeled by these H and H tilde that sit in this solution set. So this is sort of the refined conjecture that incorporates this physical constraint. And this is what we can actually prove mathematically to be true. Okay, but before getting there, let's look at a simple example. Let's look at this set of manifolds LP, minus 1 times S1. So they correspond to D2 plus D2 geometries glued together by this particular SL3Z matrix. And note, in particular, it includes the S3 cross S1 geometry. So it includes L1, minus 1, but that is essentially the same as S3 times S1. Now, if you compute the solution set of this guy, so if you compute the pairs H and H tilde that satisfy the condition, it turns out that that solution set contains an SL2Z family of compatible blocks, where H and H tilde take the same form and are just equal to a general SL2Z matrix. And this should not be surprising, because in this case, you see from the form of FP, the 001 fixes this one non-contractible cycle, but the 100 column fixes in addition the other non-contractible cycle. So we have two non-contractibles, both non-contractible cycles are fixed in the gluing, and so we can embed the time circle as any cycle inside this T2. So, so it is, in that sense, it's not surprising that there is a SL2Z family of compatible holomorphic blocks with the factorization of this indices, but for any value of P. So modular factorization in this case can be written in the following way. So I can write I can write a factorization in terms of B alpha H of rho and H of the inverse of rho is equal to this untransformed factorization. And so the reason for writing this expression is because this looks a lot like a covariance under an SL2Z action, but it's not quite the covariance that you know from ordinary modular forms, because there's, in addition to the SL2Z action on the modular sigma, in addition, you have to combine it with this action in the gluing transformation. Okay. So the precise mathematical significance of this is not entirely clear to us yet, but I thought it's a nice result. Okay, so I'm almost done. Sorry. Yeah. So we can. So as I said, so we solved this condition, this geometric condition for fixed gluing transformation in terms of pairs H and H tilde. We can also do the opposite. We can fix H and H tilde, and then solve for all the gluing transformations that are compatible with this choice of H and H tilde. So that is easy. We just take H and H tilde to the other side. So it follows that to solve F prime, F of O, you have to take F in this sandwich of F between H inverse and H tilde. And this is what I already said. Like geometrically, if you allow F to run over an entire set of these SL2Z gluing transformations, then you uniquely fix how you're going to embed the time circle. Right? Because if I allow arbitrary transformations, or arbitrary numbers in the start places, then there's only going to be one fixed cycle in the intersection of all those gluings, and that's so that explains why for if you consider an entire family of such F, that there is only a single set of holomorphic blocks compatible with the factorization of all such indices. So that's the statement here, that BH and BH tilde are the universal blocks in which this whole set of indices can be factorized, where f runs over this entire group f. And this f of H and H sub is also the maximal subset in SL3Z that can be factorized in terms of these holomorphic blocks. Because if I take f outside this H tilde, then I won't satisfy this condition. This set looks a bit funny, perhaps. This H inverse F H tilde, this sandwich. But if I take H tilde sub O equal to H, then this is just a conjugation of F by the group element of H, and that is a subgroup of SL3Z. That will be important for the final part of this talk. And so, as an example, if you want to know which indices can be factorized in terms of H equal to H tilde equal to S1 free, which is this original homomorphic block DS, and this is the subgroup Fs, which is this conjugation of F by S1 free. And this contains all the standard gluing transformations of the Hopf surface. But this, in a sense, explains why previously this function ds was used to factorize indices.
So this gives the LP1 family.
These are unique holomorphic blocks for an entire SL2Z family of gluing transformations. So
what compact geometries do they give?
Any LP comma Q times S1. So yeah, this is bound to be a bit confusing. So for a fixed set of gluing transformations, namely these guys, I have an SL2Z family of H and H tildes, which can be used to factorize them. I can also, but then now I'm fixing in some sense the allowed gluing transformations. I can also allow the gluing transformations to be general, but then I have to fix my holomorphic.
Yes. So you're saying this is the universal holomorphic block that does the trick.
For this specific subgroup, but I can think of more general subgroups in SL3Z, and then this BH will be the universal holomorphic block for that subgroup. But there's a maximal subgroup of SL3Z, but there's a strict subgroup.
But where does that subgroup matter in the final geometry?
It doesn't, because I can get the most general topologies with this subgroup already. So that's the statement that there's always a way to choose H and H tilde such that one of these circles goes around for the other.
Okay.
Yeah.
And also this cohomological obstruction you will talk about. How
Yeah, that's related to this fact that there's a maximum. I'm going to get there in the famous step. That's directly related to this fact that F is the maximal subgroup of SL3Z that can be simultaneously factorized into a common set of homomorphic blocks. That's the statement. So we prove this modular factorization conjecture, and the main ingredient for the proof is a more general set of modular properties of the elliptic gamma function that can be independently derived. So an example is this guy. So this is a free integer parameter generalization of this modular property which we saw in the introduction, which can be obtained by setting m equal to 1 and n tilde equal to 0. So this has this specific form, and it agrees precisely.
Oh.
That's
may I ask a question? It's a very nice question. So, in the gravitational feature,
yes.
if you go beyond supergravity approximation, is a way to see this factorization?
So I think already in this graph, I'll get there in the final slide, but I think already in this supergravity description there's this notion of gravitational blocks that people are talking about. That should be the gravitational dual to holomorphic blocks. So there's already a signature of this factorization in gravity, but I don't think it's really well understood, but there are some people working on this in the group of Zephyrin.
So if you do some
Supergravity normalization.
yeah.
This has not been done yet, so but I think so. This is more of an experimental. These gravitational blocks are more of an experimental observation that you can write the on-shell actions of this class of supersymmetric black holes as the gluing of two functions. So it's very simple. It reflects the holomorphic block. I think it was found by thinking about how holomorphic block factorization manifests itself at the level of the.
What were the names you just referred to? You referred to some names.
Yeah,
Zaffaroni
and various collaborators.
So I mean Hussein and Christoph.
Hussein, yeah, exactly.
But Sam, I mean, stringy states just don't contribute to the index, right?
Stringy states don't contribute at all.
Yeah. Just the supergravity states contribute.
I see.
So there is no question of going beyond supergravity.
Right. I see. Yeah. I see.
Did you turn on the projector again?
Yeah. So the index is independent of the Young scope.
Yes, that's another way to say it. Which is true, because of Witten argument.
So
that is true because of the Witten argument, standard Witten argument.
So there's so this thing is protected.
There's a light impact, so it's on.
It is.
There's no blinking yet, so.
It may take some time.
Both of these guys.
The state is not all supergravity states.
Sorry?
I mean, it's not all supergravity states.
I mean, how's it, yeah.
But you said that.
No, it's
Now it's blinking.
Stringy states don't contribute.
Oh,
Just give it some
but
time.
they're not all supergravity states.
Not all of them, just the BPS.
Yeah.
BPS states.
Which is just considered as supergravity action.
Supergravity.
Stringy.
Just supergravity multiplier contributes. This was observed already in Suraj's paper.
It's a non-repeatable, non-reproducible expression.
While it warms up, could you just completely on a different line of thought? So this relatively complicated vibration of the thermal S1 over S3. So all this is Euclidean. Does this have? Is it certain to have a Lorentzian interpretation?
No, I don't think so.
But isn't that a bit problematic? I mean, to compute a Euclidean partition function that has no Lorentzian continuation.
There's a similar story in 3 dimensions, right? In the ADS3 CFT2, where the SLQZ family of these BTZ black holes don't have a Lorentzian continuation, but still here in the Euclidean platform.
But I'd say that the boundary theory certainly has a perfectly good Lorentzian understanding, right? It's just that you're right that the bulk does not necessarily have such a thing, but that I think is fine. But here, this is just a field theory question.
Oh, sorry.
It seems to be just a field theory question.
Oh, sorry. So say it again.
So that is this S1 cross
S3.
yeah, but let's just say S3, right? But they are fibered over each other in various ways
Yes.
with the full potentials and PQs put on.
Yes.
Does that have a Lorentzian continuation within the CFT? Or is this just a strictly Euclidean CFT?
No, I think no. Because the CFT is just, let's say the n equal to 4 field or whatever. So I mean, another way of thinking of the path integral is just as an index where you just weight the generacies of states. So this, I think there is, in that sense, there is a.
If you want the time circle to be compact, you have to work in Leuven signature.
Of course.
But if you want it to be S3 times R, let's say,
Yeah.
then you could have a changing from
But I was just thinking that
This-
yes, of course, I have that as a. Yeah, this is true. It just means that I must have a killing vector direction, and I thought that this one here might obstruct those, but that's just discrete identifications.
No, but I think there is a killing factorization.
So then this is just
So
discrete.
it's not that the metric is actually not that complicated.
Yeah, I think it's complicated.
So the main ingredient in this proof of modular factorization is this elliptic gamma function. There are some additional things that I can discuss later if you want to hear about it. But this is the main thing. And the remarkable thing is that these properties that are independently derived. So the way this action on the moduli that you see there agrees precisely with this compatible diffeomorphisms in the allowed set of Heegaard splittings that we arrived at from a completely different line of argument. So this properties of the elliptic gamma function are mathematical, exact mathematical statements that use specific properties of the elliptic gamma function to prove. But I think it's a sort of remarkable agreement between these mathematical functions and this sort of physical reason at the level of the Heegaard split.
Sir, one question. Do you also get this equation, the gamma function, from SL3Z cosine
No.
condition?
No. It's also independent of that. So it uses two properties of the elliptic gamma function. But I mean, I wouldn't. Well, it's probably not independent of that. But so there is also a way to see this as a consequence of the fact that the elliptic gamma function defines a cosine.
Yeah.
But we proved it in a different way.
Sure.
But you can associate a relation to.
Yeah, that's what I was asking.
Yes. So, yeah, you can.
Yeah.
That's not the way we prove it.
Yeah, of course. Yeah. Tangential question.
Yeah. Yeah, so in fact, I mean, there's so you have this like Q equal to 1 deviation. This essentially follows from some generalization of this point.
Right.
Okay, so that brings me to the final part of the story. So it's a bit of a change of gears, but so consider a function. So I'm going to very quickly explain some mathematical notions that are very, very much geared towards what I want to say. So bear with me. So consider a function labeled by an SL3Z element that is a function of whose moduli where SL3Z acts on its moduli as we defined previously, and it satisfies that it's equal to unity on the unit element SL3Z. Then such a function defines a cohomology class in the first group cohomology of SL3Z. If it so that's a lot of technical words, but the main statement is that it has to satisfy, if this is to be true, then it has to satisfy this one co-cycle condition, namely that it's like a group holomorphism of SL3Z, satisfies this equation, which you can think of in the cohomological language as a closeness condition. Now, a locally exact expression, a local trivialization, corresponds of X will correspond to an expression the cosine of x of t, they can be written as the ratio between some function b and the function b evaluated at g inverse rho. This is exact. Why is this exact? Well, one way to see that is that this one co-cycle condition above is trivially satisfied if you plug this in for x. But if x defines a non-trivial cohomology class, that means in this language that there is no trivialization for all g. That means there's no exact expression for all g, etc. Now, this very quick slide generalizes automorphic forms, which can be thought of as classes, as cohomology classes in the zeroth cohomology, group cohomology of the relevant automorphic group. So, so then it was proposed by Abhijit that from these lens indices, one can construct a normalized part of the lens index, which reads as follows. So you take this normalized part of the lens index as the ratio between a summand of your lens index expression, and you divide it by the summand in the S2 plus T2 index of that same theory. And the proposal is that this defines a non-trivial cohomology class in H1 of SL3Z. Sorry, maybe it wasn't entirely clear. So what I've said so far is sort of a physical perspective on how you obtain a modular family of factorizations of indices. And this somehow connects to a more mathematical perspective introduced by Abhijit, that connects this to some mathematically more natural objects in this cohomology classes of SL3Z. Now, we can prove this proposal based on the things I've said. In particular, the modular factorization, if you plug in the modular factorization in the definition of this index, then you find that if you want to compute the normalized index for some g in this subgroup fh of SL3Z, then if you plug in the definition, you get that this factorized holomorphic block factorization of the numerator and denominator corresponds to a trivialization or locally exact expression for the normalized index. So that's the statement here. So the factorization of an index in terms of this function ph corresponds to the trivialization of z hat on the subgroup f of h. Because, as we've argued, that the subgroup fh is maximal in the sense that indices associated to this subgroup, so it's only indices associated to the subgroup that admit simultaneous factorization in terms of the holomorphic blocks labeled as an element h. This implies that the normalized index is non-trivial in cohomology because we can only locally trivialize it. So, okay. I'm sorry if that was a bit quick. In any case, let me conclude. So, we've seen that these ambiguities in the Heegaard splitting lead to the modular factorization of lens indices. Not all possible Heegaard splittings are realized, and the compatible blocks are parametrized by all the possible embeddings of the time circle in this gluing, such that it's left invariant in the resulting gluing. And I've also shown in an example that when this solution set embeds as a subgroup, then this modular factorization looks like a covariance, but not a standard covariance. It's only a covariance or a combined action on both the modular and the Leuven transformation. And finally, this restricted compatibility of blocks with Leuven transformations, with the factorization indices, that is related to the non-triviality of the cohomology. Now, the future directions that we hope to explore is, first of all, this related to this question of alliance. So there's some notion of the gravitational dual of holomorphic block factorization, which has been studied in works of Sofferoni and which are dubbed gravitational blocks. And so we'd like to understand if there's some more general version of that story, where now we have this whole modular family of factorizations as opposed to this original one. We can also see that family in the gravitational dual. And sort of related to that is that the original modular property that I showed in the introduction connects with the standard BPS-5 black hole. So can we somehow can we construct these more general factorizations, which will lead to different asymptotics of the index? Can we understand those and also all of those limits, understand them in terms of Bogue solutions? And do they, in a sense, classify the Bogue solutions? A subset of the solutions that definitely appears already in the work of Algoni and Benin, but not all, but not the most general factorizations that we find. I don't think the gravitational solutions associated with those have been constructed yet. And then there's also this question of, is there some type of analog of the Poincaré series for this modular factorization set? And on the SCFP side, it would be nice if there's a better matching between the physically and mathematically natural objects. So on the physics side, the indices and the factorization is a natural thing to consider. On the mathematical side, you have these cohomology groups which are associated to the normalized index, which is physically a less harder to understand what the normalized index means physically. And finally, there's a known SL2Z property of the Schur index, which is a specialization of the superconformal index. And the question is if the physical or geometric origin of that can be viewed as coming from this modular